Okay, I'm going to make a series of short videos summarising, reminding you of the mechanisms you need to know for IB chemistry this year. Okay, the first one I'm going to look at is the free radical substitution mechanism. You can go back and have a look at the full lesson if you want to. It's all there for you to find. But let's go through the mechanism directly, get straight to it. If you take an alkane or a molecule that's got an alkyl group hanging from it, so for example, you can do this also with, say, a benzene with an ethyl chain hanging off it. It can react in the same way, cross that out. But anytime we've got an alkane or an alkyl side chain, it can react with a halogen to form the halogenoalkane and HCl. So in other words, one and potentially more of these hydrogens could be swapped for a halogen, in this case Cl, but it works with Br2 as well. That only works in the presence of ultraviolet light, so you can do this on a windowsill because daylight will shine at it and UV will be absorbed and the reaction will work. It doesn't work in the dark, importantly. Now, you have to know steps of this, so all that's happening really is that H there ends up over here, and one of these chlorines ends up here, and the other chlorine ends up on the HCl, right? So what's going on there? So the first thing is the initiation, and you're expected to know the term initiation, and that causes the chlorine-chlorine or the bromine-bromine bond, which is quite long and quite weak, and it's long and weak because they're big atoms and it's a single bond, can be broken. It just so happens to have about the energy, same energy of ultraviolet light, and it will cause that bond to break. So that bond is a covalent bond. Covalent bond is a shared pair of electrons. One of those electrons ends up back on the chlorine over here, the other one ends up on over here. So we end up with two chlorine atoms, but we draw them like this now. So all it is a chlorine atom, right? Or two of them. And a chlorine atom has got 7 electrons in the outer shell. And we show that it's a radical by putting a dot there. What we mean by radical is it's got an unpaired electron. That's what's going on there. So you might be asked to define covalent bond, you might be asked to define radical, you might be asked to recognize an unpaired electron and recognize why that's so reactive. Again, that happens in the presence of UV, and you'd be expected to write out this initiation step showing the arrows there and showing UV light there. You'd also be expected to know that that's what we call homolytic. Same, lytic means splitting or breaking apart, cleavage or fission, okay? Breaking that bond homolytically. In other words, one electron goes one way, one electron goes the other way. There's such thing as heterolytic fission. Look up what that is too. Step 2, well, let's call it what it really is, which is propagation 1. Propagation 1. Now that involves one of these two reactants. So keep in mind the overall reaction when you're trying to work out the mechanism under the pressure of an exam. That chlorine radical that's produced, highly reactive, is going to react with one of these two things. It could, by the way, react with the chlorine, but nothing will happen. That's explained fully in the full lesson. But we need to know that it will react with the methane. So it will react with the chlorine, giving nothing different. But it will react with the methane productively. In other words, it will produce something different. So I'm just going to write it out like this. You don't need to draw. You might see on different videos and books full mechanisms, lots of curly arrows going on. You don't need to show those. But the chlorine radical will react with the methane or the alkyl group, whatever it might be, and cause a carbon-hydrogen bond to break. The carbon-hydrogen bonds are quite stable. They don't break very easily. But they break and you're left with what we call a methyl radical and HCl. This is, I think, the hardest step to remember. It's just one of the chlorines and it reacts with the methane. It has to react with one of the two reactants. Propagation 2, the second step, is what happens to this thing. This thing is now highly reactive and it's knocking around and it's going to react with one of the two reactants we've got up there. Well, it ain't going to be methyl because that was all involved in step 1. Again, we talk about in the longer version of this video what happens to that methyl radical if it bumps into a methane, I think. but the CH3 radical, which is highly reactive, reacts with Cl2. In other words, it rips apart this bond. It kind of causes something like that to happen. The carbon makes a bond with the chlorine. This carbon, which is a radical, it's got an unpaired electron, takes the chlorine from the Cl2, making one of the two products. The first product was made in the first step, the second product was made in the second step, and that would leave you with another radical, Cl dot. Now, what I didn't say in much detail here, or at all here, is that you only need a little bit of UV to make a little bit of Cl dot. And as soon as you've got a little bit of Cl dot, this reaction will proceed, and it will proceed, and it will go on and on and on. Because as long as you've got Cl dot, that will be used in the first step, and then produced again in the second step. And so then step 1 happens again, step 2 happens again, over and over again, maybe hundreds or thousands of times. It will only stop happening when we start to run out of the reactants, and that's when the termination steps start to kick in, and you often only need to remember one of these. I think my favourite one to remember, personally, is when two methyl radicals, maybe they've stopped bumping into Cl2, maybe it's just run out, and those two methyl radicals simply combine together, make a covalent bond between there and there, right, to make ethane. That, by the way, is a piece of evidence to show that radical chemistry is taking place. You can't get that taking place if it's a 2-electron change. It's a single electron process. Anyway, another one that you might have learnt, which is equally valid, is one of those Cl dots that's knocking around, and one of the methyl groups that's knocking around from here, bump into each other, and they will form the same product as you get anyway in step 2. And then the third one that could happen is the two chlorine radicals bump into each other. And that might happen, say, if you run out of the alkane that's present. And that's it. That's what you need to know. But just for the last few moments, I'll just make a point that you could just as easily do this with methane, but you could, as I said at the start, do with this molecule, which has got a benzene ring and an ethyl chain on it, so you could react that with bromine in the presence of, not in the dark, but in the presence of ultraviolet light. And that could, and one is more likely than the other for reasons I'm not going to get into, but that could give you a bromine there, say. They don't tend to react on double bonds or on benzene rings. Another thing to point out to you in this last few seconds is that if you've got a molecule, say, let's say you've got propene, and you get the reaction with chlorine under UV, yes, you might get one of the hydrogens, say on this carbon here, is replaced with a chlorine, and you get HCl, but then this can react again, this molecule can react again. There's still 3, 4, 5, 6, 7 more hydrogens that can react, and so it can go on to react multiple times. It's one of the issues with this mechanism. You can, or this process, you can get 2, 3, 4, 5, 6 chlorines present. That's where I'll stop. Thank you. Hope that was useful.